Hello everybody, welcome to my tutorial for implicit functions. So if you look at the picture on the right hand side, that is a circle with a radius of 10. If we're looking at the equation of what that circle would be x squared plus y squared equals 100, given your equation for a circle. So this is the easiest implicit function to look at because it gives you an idea of what is going on with implicit functions. Because a circle by itself is not a function, because if you're looking at any of your x values except for the n values, you're going to get two values for every x. You're going to get two y's, and that clearly is not a function, because for a function for every x, you just have to have one y, and it's going to break our semi-vertical line test there. So that is not a function by itself, but you can, if you do look at it in terms of just one half of it, the top half, or the bottom half, either one, it will be a function. So the top half itself will be a function, and the bottom half itself will be a function. So what we're looking at when we look at it in terms of calculus is what is the rate of change going to be at any particular point in this function. So we can do that given this equation. So say I want to find a point here, any point x, y, and I want to know what the value of the derivative is going to be. Well, the derivative we know is the instantaneous rate of change, or it is the slope of a tangent line. So this tangent line is clearly going to have some sort of slope, and it's clearly going to be negative, so we need to know what that's going to be. So we need to be able to take the derivative of these functions, either split them up, which can get to be very difficult if the function is complicated, or in terms of this function, it would be kind of easy, but we want to blanket all of these implicit functions just to get the derivative. So the first one is easy. We should know how to get the derivative of x squared. It's just our power rule, and that is going to be the derivative of that term is just simply going to be 2x. So where it gets a little bit complicated is when we look at y squared. So the derivative of y squared, I can still use the power rule, but in terms of what I'm using here, I need to use really my power rule and then my chain rule, because y is a function. I could solve this whole thing for y, and that would in itself be a function. So I need to take that into account. So I need to say that I'm going to take the derivative of what's inside. So what's the derivative of what's inside? Well, the derivative of what's inside, I can just sort of shorthand that and say it's dy dx. And that's kind of nice, because not only did I take the derivative of y with respect to x, which is what that means, but now I've taken the derivative of this whole thing after I take the derivative of 100. Since 100 is a constant, that is going to be 0. So what I can do here is now I can isolate this as this dy dx as the term that I need to solve for. So solving for that is pretty easy. I just subtract 2x from both sides. That gives me 2y dy dx is equal to negative 2x. And then I divide by 2y on both sides. And that gives me kind of a nice little fraction of negative x over y. So if I'm looking at this point on the function, and I can come up with a point on the function of 6. If you square 6 and 8, is that going to give you 100? 6 squared is 36. 8 squared is 64. Oops, I mean 100, not 8. And 36 plus 64 is going to give you 100. So that checks out. So at the point 6, 8, and many other lattice points or integer number points, you're going to get a point that works. So I want to know what's going on there at 6, 8. What is the instantaneous rate of change, and what is the slope of a tangent line? So if 6 is my x and 8 is my y, I simply plug it into my derivative formula. So x is 6, y is 8, and reducing is going to give me 3/4 negative. The derivative at that 0.68 is going to be negative 3/4.